Unpolarized light. In unpolarized light, the fluctuations in the electric field occur in all directions. It's random. As you can see here, the light beam goes one way, but those various electric field fluctuations occur in many directions. This would be an example of most of the light we see, light from a light bulb or light from the sun, say. Polarized light. Because light is a transverse wave, it can be polarized. Longitudinal waves can't. In polarized light, the electric field vibrates in only one direction. As you can see here, compared to the direction of wave motion, the light is only vibrating in one particular direction. This is polarized light. Polarizers. Unpolarized or random light can be made to be polarized with the aid of a type of filter. Take our unpolarized random light here, pass it through a polarizing filter, and the result out the other side is polarized light. This polarizing filter acts like a grate or strain that allows only one direction of motion. A good analogy is a picket fence and a rope. Imagine you have a rope passing through the slot in a picket fence. You can shake or vibrate that rope in any direction. However, once it goes through the picket fence, the slots, which have a particular orientation, allow only one direction of motion to pass through. Pairs of polarizers. A pair of polarizing filters can be used to precisely adjust the intensity of a light source. With these two pairs of filters, we can arrive at just the amount of light that we would like. The end result is polarized light of a particular reduced intensity, depending upon how we orient the filters. Intensity adjusting polarizers. With the pair of polarizing filters at a 0-degree angle with each other, in other words, parallel to each other, a maximum amount of light emerges. On the contrary, with a pair of polarizing filters set at a 90-degree angle to each other, perpendicular, a minimum amount of light emerges, virtually none. So, by adjusting the angle between the direction of the two filters, between 0 and 90 degrees, the intensity of the light can be controlled. Malice's law. This law describes how the angle between a pair of polarizers affects the average intensity, or strength, of the light, just as we previously described. S bar equals S0 bar cosine squared of theta. The S0 bar is the original average intensity of light in units of watts per square meter. The S bar is the reduced average intensity of light in watts per square meter. And the angle theta is the angle between the two polarizing filter axes. Malice's law example. If two polarizing filters were to be used to cut the intensity of light to 1/2 of its original value, how should they be arranged? We'll be using Malice's law, but we won't be finding the reduced intensity. That's already given in the problem. We'll be looking for the angle to achieve that characteristic 1/2 intensity of light. Malice's law solution. Start with our formula, but in this case, we're looking to find the angle. So rearrange to solve for theta. Divide both sides by S0. Then take the square root of both sides. Finally, since we're interested in the angle, not the cosine, we'll need to take the inverse cosine of both sides. Once we've rearranged our formula, we can substitute in our values. Actual values weren't given, but we can use 1 as our original intensity and 1/2 as our reduced intensity. This gives us a value of 45 degrees, which should seem kind of intuitive, because after all, 45 degrees would be halfway between complete transmission and zero transmission. And we are cutting the light intensity by 1/2.